Hello everyone and hello to all my young friends who are studying in intermediate and they are watching this video. My name is Salman and very recently I started this online educational platform. The topic which I am going to discuss is from mathematics and the name of the topic is derangement. Derangement is a topic which is taught under the chapter of permutation and combination, and it's a very interesting topic. In fact, the whole permutation and combination itself is quite interesting. Uh, so we'll start derangement. Now, what does derangement mean? I'll give you an example. At times, when we make a mess of the things in our room, just scatter the objects here and there, and our mom or dad, they are quite angry when they come to our room after seeing everything scattered, and they make a statement, "What have you done?" Nothing is at its place. Now, this statement, nothing is at its place, that is what is called derangement. In truly mathematical sense, when our mom and dad makes this statement, it may not be a perfect derangement, but perfect derangement means that if you have n things in a room and you have place for all n things, but none of the thing occupies the place meant for it, that is called derangement. So today we will learn what does derangement mean in truly mathematical sense, and is there any formula to calculate the number of derangements of say n number of things, and how do we derive that formula. So please pay full attention. This is going to be very interesting also. But before understanding derangement, let's revisit a bit of permutation combination. I think you must have read a bit about permutation combination. Anyway, I presume that you have not read about it. So I'm again revisiting those very basic concepts. Now, combination of n things taking r at a time, that is denoted by NCR, and that is equal to factorial n upon factorial n minus r factorial r. You must be knowing factorial. For example, factorial 5 means 5 into 4 into 3 into 2 into 1. And one more important thing is factorial 0 is defined as 1. So combination of n things taking r at a time, the formula is denoted by NCR, and this is the formula. Let me give you an example, it will be more clear. For example, if you have to choose a team of 4 people and you have 10 people and you have to choose a team of 4. So number of combinations will be factorial 10 upon factorial 10 minus 4 factorial 4, means 10C4. So that's going to be factorial 10 is 10 into 9 into 8 into 7, and here you can write factorial 6 because in denominator 10 minus 4 is, this is factorial 6, and factorial 4 is 4 into 3 into 2 into 1. So this gets cancelled. 3 is a 9, and 4 and 2 gets cancelled from here. So 7 3 is a 21 into 10, 210. So this is the answer. I hope it is clear to you. Now, permutations of n things taking r at a time. What do we mean by that? If there are n things and we take r at a time, so how many ways in how many ways they can be made to sit at different places, how many ways they can be arranged at different places. That is called permutation. For example, we have 1, 2, and 3. So permutations are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. These are called permutations. So if you have n things and you are taking r at a time, so a formula is npr, and that is equal to factorial n upon factorial n minus r. One example will make it more clear. Number of ways, suppose you 8 friends go and take a snap, and you are taking a snap having 4 people at a time. So the number of permutations are 8p4, which means factorial 8 upon factorial 8 minus 4. That is 8 into 7 into 6 into 5 and factorial 4, and denominator it is factorial 4, so this gets cancelled. So then you get 6 5s are 30, 3 7 are 210 into 8, that comes to 81680. So that is the answer. I hope you got an idea of what is permutation and what is combination, because we'll be using it. That is the reason I'm telling you here. Now, if we are taking all at a time, means we have n things and we are taking all at a time, then the permutation becomes n p n, which is equal to factorial n upon factorial n minus n, which is equal to factorial n upon factorial 0, and this is defined as 1, so that is factorial n. So permutation of n things taking all at a time is factorial n. Let me give you an example. If there are 5 friends and they go for a photographs and taking all at a time, what are the number of permutations? So that is 5p5, which is equal to factorial 5. That is 5 into 4 into 3 into 2 into 1. That means 20 into 3 2s are 6. That is 120. I hope this is clear, and we'll proceed further. Now let me tell you what is derangement mathematically with some example. For example, if we have 3 numbers 1, 2 and 3. Now they can be written as in correct order 1, 2 and 3. This is the place of 1, this is the place of 2, and this is the place of 3. Now I have already told you that we can permute this in factorial 3 ways, that is 6. That is 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So these are the 6 ways. In this you have every number at its correct place. Here you have 1 at its correct place and 3, 2 are not at their correct place. Anyway, we'll depict by some colors. Green means all at correct place. Blue indicates 1 at its correct place. Red, none of the number is at its correct place. Now 1, 2, 3, every number is at its correct place. Here 1 is at its correct place, 3 and 2 are not at their correct place, neither this nor this. Here 3 is at its correct place, 1 and 2 not at their correct place. Here none of the number is at its correct place, that is why I have marked in red. Here again none of the number is at its correct place. And here 2 is at its correct place, 1 and 3 are not at their correct place. So these are 6 total permutations, 6 in number. Out of that, you have 2 derangements. Now, if we have 4 numbers, similarly, what we did with 3 numbers, we'll do it here with 4 numbers. Again, we'll use one more purple color indicating 2 at its correct place, and red, none is at its correct place. So total permutation will be factorial 4, which will be 4 into 3 into 2, 24. So we'll write them here. Now you can see here, in one permutation, every number is at its correct place. It will be 1 only. Then here, 1 and 2 correct place, 4 and 3 are not at their correct place. Similarly, you can see for other. If you want, you can just pause the video and see. Now here, how many derangements? They are marked in red. 1, 2, 3, 4, 5, 6, 7, 8, 9. So out of 24, you have 9 derangements. I hope now it is clear as to what do we mean by derangement. Now, if we have 3 numbers or 4 numbers or even 5, we can do it like that. But if we have more, it's not possible. That means we have to have some formula which gives us the number. So is there any formula? There is one formula. First of all, I'll tell you what is the formula, and then we'll go for deriving that. So formula says, if there are n things in a row, a permutation of these n things such that none of them occupies its original position, this is called derangement, and formula is factorial n, 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4 minus 1 upon factorial 5 and so on, plus minus 1 raised to the power n, 1 upon factorial n. So you can see here you have 2, you just write minus 1 raised to the power 2, so sign will be plus. Here 3 minus 1 raised to the power 3, sign will be minus 1 raised to the power, here you have 4, so sign will be plus, minus 1 raised to the power 5, sign will be minus. Hence, if it is n, we have written minus 1 raised to the power n. Now, we have just found out if there are 3 things, we got 2 derangements, and if there are 4 things, we got 9 derangements. This is just the 2 examples which I discussed just now. Now let us check whether this formula is correct or not. For first case, that is 3 things. N is 3, factorial 3, 1 upon factorial 2 minus 1 upon factorial 3. It comes to 6, 1 upon 2 minus 1 upon 6. Take 6 as LCM. 6, 2, 3 minus 1. Cancel 2. So this is correct. For 3, it is correct. Now for 4, we got 9 derangements. Just check it for 4. Factorial 4, 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4. That means factorial 4 and then 1 upon 2 minus 1 upon 3 to the 6 minus factorial 4 is 24. So again you take factorial 4 as an LCM, so it gets cancelled. So this becomes 12 minus 4 minus 1, which comes to how much? It's plus, sorry. So it comes to 9. So this is also correct for 4. Now we will do the derivation, or you can see we'll learn how this formula is derived. But before deriving the formula of derangement, let's recall union of sets. What is union of sets? If there are two sets A and B, A union B is equal to set A plus set B minus A intersection B. Let me explain it by Venn diagram. This is your set A, this is your set B. So say this whole area is 1, the other area is 2, this third intersection is 3. Now set A is 1 and 3, set B is 3 and 2. Now what is A union B? Means taking all elements which are there in A and B, only one at a time. Means 1, 2 and 3. Now A intersection B is 3. Now A union B is 1, 2, 3. So the formula is A union B is equal to A plus B, because if you add A and B, what will become? 1, 3, 3, 2. So 3 gets repeated. So you have to delete 1, 3. That means you have to subtract A intersection B from here. This is for 2 sets. Now we'll see for 3 sets. Now if there are 3 sets, then A union B union C is A plus B plus C. Add all of them. Then subtract intersection of 2 sets, the sum of all these kinds of sets, and plus add intersection of 3 sets, all the set. That means if this is A, B, C, mark all this area like 1, 2, 3, 4, 5, 6, 7. Now A is 1, 4, 5, 7. Similarly, B is 2, 4, 6, 7. C is 3, 5, 6, 7. A intersection B is this one, 4, 7. B intersection C is 6, 7. C intersection A is 5, 7. And the intersection of A, B and C is only this, that is 7. Now if you take A union B union C, you will take 1, 2, 3, 4, 5, 6, 7. This will be A union B union C. Now the formula says we have to add all of them. So now just add. So what will happen? 1, 4, 5, 7, 2, 4, 6, 7, 3, 5, 6, 7. But here 4 is being repeated, 5 is being repeated, 6. So many are being repeated. So what we have to do is we have to subtract them. So how do we do that? Now, you have to subtract all these intersections. A intersection B is 4, 7. 4 and 7 gets cancelled. B intersection C is 6, 7. C intersection A is 5, 7. They all get cancelled. So we are left with 1, 2, 3, 4, 5, and 6. But we have to have 7 also. And 7 is A intersection B intersection C. So what we have to do? We have to add A intersection B intersection C. This is for 3 sets, but the formula for n number of sets, if there are n number of sets, and you take the union A1, A2, A3 till An, this is, you have to take all the sets first, then subtract intersection of 2 sets, then add intersection of 3 sets, then again subtract intersection of 4 sets. Similarly, minus 1 raised to the power n plus 1. Why? Here we are taking 2. Here we are taking one set at a time. That means minus 1 raised to the power 1 plus 1. Then it will become plus here. Here we are taking 2, so minus 1 raised to the power 2 plus 1. Then this will be minus. Here we are taking 3, so minus 1 raised to the power 3 will be minus, plus 1, that will be plus. Hence, if we are taking n, minus 1 raised to the power n plus 1. So that is why we have taken like this. So this is the general formula. Now this A1 plus A2 till An can also be written sigma A1. This can be written as this whole can be written as sigma A1 intersection A2, right? Like this. And this set can be written as sigma A1 intersection A2 intersection A3, right? We can write it like this. So we can also write this formula in this manner. Same, but a bit easier way. You don't have to write so many terms. So I hope this is clear. Now let's again recall the 2 examples which we discussed initially. That is derangement of 3 numbers. This is what we discussed while starting this topic. Now for these 3 numbers, what are the total permutations? That is factorial 3, that is 6. Just draw the Venn diagram. So these are the 6 cases. Total number of arrangements, factorial 3, that is 6. We will arrange them in a more proper manner. Just see how. Now we take one set where 1 is at its correct place, and we call that set as A. That means set A are the permutations where 1 is in its correct position. So which will be there? 1, 2, 3, this one and this one. Right. Then B is the set of permutation where 2 is at its correct place. One element is already there, which is shown in intersection. The other is 3, 2, 1. C, where 3 is in its correct place. So it will be 2, 1, 3. So now how many elements? 1, 2, 3, 4. There is nothing common here, so we'll just modify our figure. Now it looks better. Now, where are the remaining which do not find any place here in this? There are two which will be outside. Okay. Now, what does this figure depict? Just think for a while. I think you must have got some clue. That means if we subtract union of all these sets A, B, and C from the total numbers in the set, we will get the derangement. That is, factorial 3 is the total arrangements, and you subtract these four numbers, that is union A, union B, union C, then you will get the derangement. Right. Again, we take the other example. A, 1 is at its correct place, B, 2 is in its correct place, C, 3 is in its correct place, and D, 4 in its correct place. Now, what was the total number? Factorial 4, which was 24. But how many we find here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many are less? 9. They are the derangements. They will be outside. So that means again, number of derangements are factorial 4, the total, permutation which were 24, and you have to subtract these 15 elements. That means if we subtract A union B union C union D, what does that mean? At least one arrangement, at least one is at its place, and it is 2 may be there or more than that. But at least in all these, numbers, in these 15 numbers, at least one element, one number is at its correct place. Somewhere 2 are also, and all the 4 are also there. Because if 3 are at its correct place, fourth one will always be at its correct place. That means, now we got a clue here. If from the total permutations, we subtract the set of at least one arrangement, which is nothing but A union B union C union D, where A, B, C means one number is at its correct place, the union of all these sets, then we'll get the derangement. Now we go to the proof. Till now we have discussed 3 numbers, 4 numbers, but if there are n numbers, A1, A2, or n elements, whatever you call, n things, n elements, whatever, A1, A2, A3 till An. Again, we'll say number of permutations will be factorial n, because that is total permutation. Now you have to subtract what? Suppose S1 is the set of all permutation where A1 is at its correct place, S2 where A2 is at its correct place, S3, S4 till Sn means set of all permutation where An is at its correct place. So how will you get the derangement? You have to subtract S1 union S2 till Sn from factorial n. Means from factorial n, you have to subtract the union of all these sets, S1, S2, S3 till Sn. Now the question is how to calculate or how to find this union. Okay. So S1 union S2 union S3 till Sn. We already discussed that this is sigma S1 intersection S2, sigma S1 intersection S2 intersection S3, and so on. We already have discussed, so no need of discussing it once again. Now we have to find, that means this expression, and then we have to subtract it from factorial n. Now comes one more interesting part. Now sigma S1 means this term. This is S1 plus S2 plus S3 plus Sn. Suppose S1 is at its correct place. How many are remaining? N minus 1 elements. So they can be arranged in factorial n minus 1 ways. Here S2 is at its correct place, remaining factorial n minus 1 ways. S3 is at its correct place, remaining in factorial n minus 1 ways. Similarly, Sn is at its correct place, remaining can be arranged into factorial n minus 1. Now, what is the number S1, S2, S3 till Sn? We have to take combination of n things, taking one at a time, which is nothing but n, but we will write nc1 because nc1 is n. How? Factorial n upon factorial n minus 1 factorial 1, which is nothing but n. So this will become nc1, total number 1, 2 till this n, into factorial n minus 1, right? So now what will be this term? Sigma S1 intersection S2. Now if you have put 2 at its correct place, then the remaining can be arranged into factorial n minus 2 ways. Here also factorial n minus 2. And what is the number of these terms? 1, 2. Combination of n things taking 2 at a time, and every term will have factorial n minus 2 elements. This one. So similarly for 3, and so on. If everything is at its correct place, means S1 intersection S2 till Sn, this will be 1, but we write in this form only. It will be n Cn factorial n minus n, which again is factorial n upon factorial n minus n 0, factorial 0 and factorial n, and this is factorial 0, so this is 1, but we'll keep it written in this form only. Now you got a clear idea as to how to find this term. So maximum part is over now. That means this is equal to nc1 factorial n minus 1 minus nc2 factorial n minus 2, and so on like this. Now we have to subtract this from factorial n. How much is this? Just see. Factorial n upon factorial n minus 1 factorial 1 into factorial n minus 1. This gets cancelled. So this will be factorial n. So this will be how much? Factorial n. What is this term? Factorial n nc2 factorial n upon factorial n minus 2 factorial 2, and then you have factorial n minus 2 like this. So this will get cancelled. Factorial n upon factorial 2. Similarly, this is factorial n upon factorial 3. So this will be factorial n minus, you have to subtract this whole expression from factorial n to get the derangement. This will be factorial n upon factorial 1 means factorial n minus factorial n upon factorial 2 plus factorial n upon factorial 3 plus and so on plus minus 1 raised to the power n plus 1 factorial n upon factorial n, right? Now when you subtract, this will be factorial n minus factorial n, this will get cancelled, plus factorial n upon factorial 2 minus factorial n upon factorial 3 plus factorial n upon factorial 4 and so on, and this minus 1 raised to the power n plus 1, now you can write it as minus 1 raised to the power n, because when again 1 minus will be multiplied, so it will be n plus 2 and you can remove that 2, factorial n upon factorial n. Now this will get cancelled, take factorial n as common, 1 upon factorial 2 minus 1 upon factorial 3 and so on. So we write this formula like this. I hope it is clear, the derivation part. Now let us do one or two questions. Find the number of ways in which 4 letters can be put in 4 addressed envelopes so that no letter goes into the envelope meant for it. That is derangement. There are 4 letters. Letter 1, letter 2, letter 3 and letter 4. Now we have 4 envelopes, E1 for L1, E2 for L2, E3 for L3, E4 for L4. So we have to keep L1 in E1, L2 in E2, L3 in E3. Now he is asking no letter goes in the envelope meant for it, that means it is derangement. The formula is factorial 4 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4, and this is equal to 9. So 9 is the answer. We did a similar question, so no need of doing again the same calculation. Now there is one more problem. There are 7 groups in a picnic who has brought their own lunch box, and one group carries one big lunch box for all the people in the group, and these 7 big lunch boxes are kept and then they are distributed to the groups. Now what happens? None of the group get their lunch box. That means it's a derangement of 7 things. That's 7 lunch boxes. The formula is factorial 7 1 upon factorial 2 minus 1 upon factorial 3 plus 1 upon factorial 4 minus 1 upon factorial 5 plus 1 upon factorial 6 minus 1 upon factorial 7. It's a bit lengthy calculation. The answer is 1854, and now I leave it to you to do this calculation. Take it as a exercise at your end. So that's all in derangement, and I hope you enjoyed this. Thanks for watching this video. Have a nice day.